in the previous chapter, what you guys learned was dual nature of matter, right? That means a matter, it behaves both as wave as well as a particle. So we learned about that. It was very simple that how a particle such as an electron, it could behave like a particle as well as a wave, right? Now, from that very small particle, let's say we come across the next topic, that is, what if we have those small particles grouped together? That means electrons are grouping together with protons and neutrons. We get atom, correct? Now, let's go into one step further of an electron, or that we are looking at the atomic scale now. Alright? Now, very first thing about the atomic scale is that, see, atomic scale, when we say atomic scale, it's very small, it's very minute. Now, if we have to look at it from the history point of view, John Dalton, he was the first one who said that atoms are indivisible particles, right? Then after Dalton, then we have Thomson, that is Thomson's pudding model. Then after that, his student Rutherford, he made a lot of contribution to the field of atomic physics. Then his student Niels Bohr, he also made a lot of contribution to this atomic physics. Then after Niels Bohr, then we have Schrödinger, Erwin Schrödinger. So that fellow also, he did a lot of things for atomic physics. Alright, so the names what I'm telling, they're all pioneers in the atomic physics. They have done so many things for atomic physics. Okay. Now so this is the, you can say, the history of the atomic physics. Alright, now let's look at the introduction as to what we have in this particular chapter. Now, very basic things, that is, you're going to learn what consists of, like, what is there in an atom. Atom consists of what? Very basic answer, we have protons, neutrons, electrons. Yeah. But then you're going to learn a little more detail about how these atoms, how this nucleus was discovered, and what do you mean by these electrons, and how we are going to use this. Okay, use as in the practical application of these electrons. I'm not just talking about the current. There are so many other applications. Electron microscope is there. So many applications are there. Alright. Now, let's talk about what Dalton did. So John Dalton, he's John Dalton. Now, during his era, during his period, not many technological advancements had happened so far. So there was no further improvement, or you can say there was no further division of atom. So he just gave a statement that atom is the smallest particle ever and it cannot be divided. Okay, but then as the technology improved, there was a lot of advancements. Then J.J. Thomson, so J.J. Thomson, the discoverer of electron, he gave an atomic model. Okay, so this is what we call as Thomson's pudding model. Okay, this is Thomson's pudding model. Now what he told that atom is like a positively charged jelly, okay, jelly like substance, and in between there are electrons which are static, like, you know, a plum pudding. So inside the pudding you have all those seeds kind of thing. So this is Thomson's plum pudding model. But then Thomson's model had a lot of ups and downs in it. One thing what he could clearly explain was all atoms are electrically neutral. He could explain the neutrality of atom using his model. But he failed to explain a lot of other things. Like he could not explain the orbits, he could not explain the charge to mass ratio, so many other parameters he could not explain. Okay. So Thomson's model failed. Then comes the most interesting model, that is Rutherford's model. Alright, now let's talk about the Rutherford's model. So when we say Rutherford's model, see, a lot of experiments, most of them were trial and error. Because atoms are so small, it's microscopic, it's submicroscopic, you can't really see it. So everything has to be done as an experiment, that too most of them were trial and error method. Alright. So what Rutherford did was, so he he took one radioactive source. See, when we say radioactive source, we have alpha, beta, gamma, so many radiations will be coming, right? So one radioactive source, and he kept it in a lead box. See, lead, we use it because lead absorbs all the radiation. Then a small cavity was made so that all the radiations escape. Alright, then this was made to come in a straight line, and it was made to hit a very thin gold foil. Okay, the thickness of the gold foil was around a micrometer. 10 microns is what we say. Okay, 10 microns, that is 10 power minus 5 meter. This was the thickness of the gold foil. And then, so see, we need to know how this alpha particle, or what exactly is going to happen in experiment, the result. For that, a photographic plate was kept around it. Okay, so that photographic plate, it was coated by zinc sulfide. Zinc sulfide has a property that whenever an ion or any charged particle comes in contact with it, it glows. Okay, like a fluorescent green color light will come, it glows basically. Excitation of atoms, excitation of electrons and everything. So basically this is the experimental setup. Clear? Now what's going to happen? We'll see the experiment. It's very simple. So an alpha particle from the radioactive source, it passes through the cavity and it hits the gold foil. Alright, and then all those alpha particles were scattered and they were all caught by this particular photographic plate. So when I say caught by it, it's not catching exactly, in the sense the alpha particle hits the plate and then you can see the detection, the fluorescent green color detection. This was Rutherford's alpha ray scattering experiment. Okay, this is the experiment. Now see, alpha particle hits the gold foil and it scatters. Correct? This is the whole experiment. But then this experiment, it changed the overall perspective of how we saw atomic physics. Because this gave up to doors of so many opportunities opened up because of this experiment. So let's see what experimental observations were made by Rutherford. Okay. Now experimental observations, see, there are two things. One is we do experimental observation. Second is we do the theoretical counterpart of it. What we see from the experiment, then we theorize it. Okay, theoretically we try to do. So experimental observations, what he saw, what Rutherford saw, was that most of the alpha particles, they went just straight through the gold foil. Most of it, okay, about 90% of it. So he came to a conclusion that most of it, that means, see, most of them are going through it, that means it has to be empty. So this was one of the observations what he did. The next observation was, very few of them were actually scattered. Okay, everywhere they were scattered. Alright, that means there has to be some particle which is actually deflecting these alpha particles. Then the third thing what he saw was very, very few, that is 1 in 8,000, that's about 0.0125%. Just try to understand, 1 in 8,000 alpha particles, they just retraced by 180 degrees. That means they're hitting something, they're coming back in the same direction. Correct? See, alpha particle is a helium nucleus, 2 protons and 2 neutrons. So 4 massive particles. This is around 7,000 times the size of an electron. Even the mass also. So electrons cannot deflect it. Right? It has to be some positively charged particle. Right? So he came to a conclusion by the experimental observations. And also when he plotted the graph, you can see this is the graph what we have. See, along the x-axis and along the y-axis, you can see what parameters we have. And then the graph goes like in an inverted exponential curve. Alright? These were the experimental observations. Then the theoretical part, we'll see what are the things he did.